I'm super excited to share with you my very first video on the Fibonacci numbers on my channel. So we're going to prove that if P is a prime number, doesn't matter what it is, then there are infinitely many Fibonacci numbers divisible by P. Okay, so this is going to be a very conceptual and elegant mathematical proof. It's going to be so beautiful. Use a lot of ideas to make it very nice. So let's just get into the video, and we start off with the Fibonacci numbers. I'm going to set some notation just to keep things consistent in the video. So we're going to start the Fibonacci sequence with 0 actually. This is going to be convenient for us, 0 and 1. And then of course the way the Fibonacci sequence works is you add two terms to get the next term, two consecutive terms. So 0 and 1 you add up to get 1, 1 and 1 you add up to get 2, 1 and 2 you add up to get 3, 2 and 3 you add up to get 5, and so on and so forth. Okay, 3 and 5 adds up to be 8. So we're going to label this F0, F1, F2, F3, and so on and so forth. Okay, F4, and it keeps going. These are the terms of the Fibonacci sequence, and you can define this rigorously as well. You could say that basically F0 is equal to 0, F1 is equal to 1, and then the way the Fibonacci works, the crucial way it works is that you need two terms and then you can get the next term. Okay, so it's not one term determines the next term, it's two terms determine the next term. Okay, that's how we have to think about it, and we can define Fn plus 1 is equal to Fn plus Fn minus 1. Okay, and this is going to be for n at least 1. Okay, this is how we're going to define the Fibonacci sequence. Okay, so basically what we're going to do now is we want to prove that if you take a prime number P, doesn't matter how big, P could be 17, P could be a really, really large prime number. Okay, so it could be, have many, many digits. There are infinitely many terms of the Fibonacci sequence divisible by P. Even knowing there is one term divisible by P is not totally obvious, but actually the argument for that is going to also show there are infinitely many terms divisible by P. What we're going to do, the first trick, okay, and this is like a trick in math, is the Fibonacci numbers go on forever and very, very hard to calculate, right? If you take a very large one. So we're going to try to make our infinite problem into a finite problem. Okay, this is a common idea in mathematics. So our finite problem is we're going to look at remainders when you divide by the prime number P. Okay, so I'm going to define my Fibonacci sequence Fn prime. Okay, it's a new sequence. Okay, it's going to have a prime up top to be the remainder when you divide Fn by P. Okay, so the remainder when Fn is divided by P. All right, so that's what Fn prime is, and what we want to show, okay, what this does for us is the possible remainders when you divide by P, doesn't matter what P is, are 0, 1, 2, ... P minus 1. Okay, so there are basically P minus 1, there are P choices, there are P possible remainders when you divide by P. That's a finite number. So this Fibonacci sequence doesn't go on forever. It's just going to go within this finite set of P choices. And what that means is there's going to be some repetition, okay, because there can be infinitely many Fibonacci numbers, but there can't be infinitely many possible remainders. There are only P possible remainders. So there's going to be some repetition within this. And we're going to exploit that to show that 0 is going to be a remainder. Once you know that 0 is a remainder, then you know that there is a Fibonacci number divisible by P, and then that's going to cycle and give us infinitely many Fibonacci numbers divisible by P, and that's what our approach is going to be. Now, it's very important when you're understanding this Fibonacci sequence, we need to again think about successive terms of the sequence. Okay, so we need to think about how Fn and Fn minus 1 determines Fn plus 1. So what we're going to do is we're actually going to use a little bit of matrices to make this very precise in terms of understanding this property. Okay, so I'm going to do that on this side of the board. So more precisely, as I said, because there's only a finite possible number of remainders, there has to be some I and j, so that fi prime, the remainder when you divide the ith Fibonacci number by P, is equal to fj prime, the remainder when you divide the jth Fibonacci number by P. This has to be equal for some I less than j. But that's not going to be enough for us, because just knowing the ith term of the sequence doesn't tell us the I plus first term. We have to know the I minus first term and the ith term. So for this reason, I'm going to go into the world of 2 by 2 matrices, okay? And you'll understand what this is going to solve for us, how this is going to make things conceptually simpler, because what we're going to do is we're going to think about the Fibonacci sequence in terms of matrices, and this is a very powerful thinking process, is that if we define the matrix A, so okay, I'm just going to write A as the following. A is going to be the matrix 0, 1, 1, 1. Okay, this is our matrix A. Okay, now why am I defining this matrix? Now observe that if we take the pair of consecutive Fibonacci numbers, okay, let's take the pair Fn minus 1, Fn, okay, consecutive Fibonacci numbers, and let's multiply with our matrix A. Okay, let's do 0, 1, 1, 1. Okay, now when I do this product, what's going to happen for me is that by doing the matrix product, 0, 1 times fn minus 1 fn is going to be fn here. And then this row times this column is going to be fn minus 1 plus fn. And fn minus 1 plus fn is just going to be fn plus 1. So what happens is our matrix A goes from one consecutive pair of terms in the Fibonacci sequence to the next consecutive pair of terms in the Fibonacci sequence. What this means is, in particular, if we apply this inductively, we're going to get that a power n, so I'm going to write this, a power n times f0 f1, right, times the very first term, f0 f1, the very first pair of terms in the Fibonacci sequence is going to equal to fn plus 1. But of course, we know that f0 f1 is just 0, 1. Okay, so I can even write that out here. I'm going to do that. We're just going to replace this with 0, 1. Okay, so we've got that. Now, why I'm looking at the world of pairs is, in the world of pairs, all these statements that I just gave, this is true for the Fibonacci sequence as usual. It's also true when you take remainders and you divide by p. Because if you take two numbers and add up their remainders and you divide by p, it's the same as taking each number, taking its remainder when you divide by p, and adding up those remainders, okay? That's just arithmetic modulo p in fancier language. So we can put our primes, which are just our remainders, and you divide by p, and everything is going to be true in this world. So now we're going to look at the pairs of consecutive terms of the Fibonacci sequence when you take remainders and you divide by p. So the point is, like I said, that there is a repetition when you take remainders and you divide by p. There will be a repetition of pairs, and that repetition of pairs is going to actually be what we need to show that 0 occurs as a remainder. So to be precise, what we're going to do is, we're going to look at the possible pairs of remainders when you divide by p. So if we call this fp, okay, this is mathematical notation, it's a field with p elements if you like. We don't have to think of it that way, just fp, then fp squared, right? fp squared is just pairs of possible remainders when you divide by p. Okay, fp squared is just fp times fp. Now, of course, there are going to be p squared possible such pairs, right? There's a number is going to be p squared such pairs. And what that means is that, you know, this consecutive terms of the remainders of the Fibonacci sequence has to repeat, right? When you keep on going, because there are p squared possible choices for this pair of remainders, there has to be a repetition because, you know, you're going on forever. You can't keep getting more and more possible pairs. There are only p squared in total. So what that means, therefore, is that there is two pairs that match up. Okay, so I'm going to write it out. For some I and j, instead of saying the remainders are just matching up, the pairs are matching up. Okay, so we can write that fi prime, so I'm going to write fi prime, fi plus 1 prime is going to equal to fj prime, comma fj plus 1 prime. Okay, this is going to be true for some I and j. All right, so we're just going to say this is for I less than j, right? For some I less than j, it doesn't matter. But then thinking about it in terms of linear algebra, in terms of matrices, we can basically write this as a power I times 0, 1 is equal to a power j times 0, 1, right? A power j times 0, 1. And here's the important thing. The matrix A is actually an invertible matrix. You know, you can find its determinant is -1. But another way of thinking about the invertibility is you can go backwards. If I know the nth and n plus first terms of the Fibonacci sequence, I can find, of course, the nth minus 1th and nth term, because the nth minus 1 term is subtract the nth term from the n plus first term. That's how I get the nth minus 1 term. So by being able to go backwards is basically saying our matrix is invertible. That's another way of doing that. And so therefore in this thing we can say, because I less than j, we can multiply by a power minus I on both sides, and I can put the a power j minus I on this side. We get that a power j minus I times 0, 1 is going to equal to 0, 1. Okay? But we also know that this is going to be the j minus ith term of the Fibonacci sequence. Okay, j minus ith term, j minus I plus first. These are all remainders when you divide by p. Okay, so that means that the remainder of the j minus ith term when you divide by p is actually 0. That's what we proved. And now we're going to just finalize our findings. We're going to finalize our findings, and we're just going to say, and I'm going to show you a couple of interesting side comments. Okay, so make sure to watch to really understand the proof. Okay, there's a lot of fun in this proof. So we've got that. So now we know that fj minus I prime is 0. Therefore, fj minus I is divisible by p. Okay, we got that. But how do we know that there are infinitely many terms of the Fibonacci sequence divisible by p? Well, we just apply the same reasoning. A power j minus I times 0, 1 is 0, 1. That means that a power n times j minus I, okay, if you just power a power j minus I by n, and you multiply that with 0, 1, you also get 0, 1. And that means that, of course, that this is going to equal to just the fn j minus I, ith remainder of the Fibonacci sequence, and this is going to be the fn j minus I plus first. Okay, so we're going to get that. That's going to equal to 0, 1. So therefore, we also know that this term, okay, fn times j minus I is also going to have a remainder of 0 when you divide by p. So therefore, we can say fn j minus I is also divisible by p for all n. Okay, so this is divisible by p for all n. And of course, it's important that j was greater than I. So okay, so j minus I is not 0, and we aren't just repeating f0, 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 etc. It's divisible by p for all n. Okay, this means for all n. Now, as I said, when I started out the proof, I told you that if we just look at remainders and you divide by p, we know there's a repetition, but we couldn't identify that repetition involved 0 at any stage. That was very important. So that's why I went to the world of pairs, and we start off with the pair 0, 1. We could use the sort of the matrix, the nice linear structure of the Fibonacci sequence. That was important. You needed to know something about the sequence, because obviously any sequence you could just randomly define. You could look at the remainders and you divide by p, and you wouldn't know 0 necessarily occurs. So you have to use that the Fibonacci sequence is coming from a linear recursive relation by a matrix A that had these nice properties. And I'll just show you what happens when you divide by 11. Okay, so just see what happens with the prime 11 in our proof, and it's very instructive. And this is going to be really exciting. So just have a look at this. Suppose we look at dividing by 11, remainders and you divide by 11, right? So you start the Fibonacci sequence 0, 1, 1, 2, I'm just going to keep going, 3, 5, 8, now 13, 5 plus 8 is 13, divide by 11, the remainder is 2. 8 plus 2 is 10, fine, 2 plus 10, 12, remainder when you divide by 11 is going to be 1. Okay, so you get 1, then 10 plus 1, remainder when you divide by 11 is 0, it's going to be 11, so 0. Then 0, then 1 and 0, you add up, you get 1, and then you get, again 1, and you see that your sequence has repeated. Okay, you see that your sequence has repeated. So if you look at, this is going to be the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th term. Every 10th term is going to be divisible by 11. Okay, so in this case, you can actually prove even that every 10th term of the Fibonacci sequence is divisible by 11, but also notice that not every remainder occurs when you divide by 11. For example, if you look at the remainders, what is missing? 4 is missing, 6 is missing, 7 is missing, 9 is missing. These remainders do not occur when you divide by 11. So it's not at all obvious that every remainder occurs. When we talked about the proof at the beginning, we talked about just remainders when you divide by p. It wasn't obvious 0 could be a remainder. We had to look at pairs, and we had to look at this matrix structure to see that. Okay, so I'm just giving you some more insights into the proof. Now, I've got 2 fun videos for you. My channel has every math. I love explaining math easily, conceptually, and accessibility in a fun way for everyone. So I'm going to recommend to you 2 videos. The first video, you're going to love this video, is a proof that if you pick 3 numbers, it does not matter what the numbers are, 3 numbers, okay? They're going to be 2 of them. Okay, let's call them A and B. Okay, I don't know what the numbers are. Let's just call them A and B. You pick 3 numbers. There are 2 numbers, A and B, out of them. I'm going to label them A and B. So that A cubed B minus AB cubed is actually divisible by 10. Okay, so it does not matter what 3 numbers you start off with. You can always pick 2 of them, A and B, with that property. It's a very popular video on my channel. You're going to love that video. Check it out. It's going to pop up on the screen. And another fun video with prime numbers and infinity is the proof there are infinitely many primes. You might have seen Euclid's famous proof, but have you seen Euler's, which is a window into the world of analytic number theory? Check out that video here. You're going to love it. Have an amazing day, and I'm super excited to see you in either of these 2 videos.